Topics in Post-Harvest Technology. Calculating Refrigeration Load, Part 2. Removing respiratory heat during cooling. Problem. How much refrigeration is needed to cool 100 tons of cabbage to 32 degrees Fahrenheit within 12 hours when it is initially harvested at a temperature of 80 degrees Fahrenheit? There are two considerations: sensible heat and respiratory or vital heat. Unlike sensible heat, which is due to the sun and once removed is gone, respiration continually produces heat, and the amount of heat is directly proportional to the respiration rate. Remember, respiration rate increases with temperature, so respiratory heat production also increases with temperature. For our problem, the respiration rate of the cabbage at 80 degrees will be much higher than the rate at 32 degrees Fahrenheit. However, the respiration rate will be decreasing during the cooling process. How do we account for the change in respiration and respiratory heat production during cooling? We use the respiratory rate at the midpoint temperature of cooling. Here's a figure showing the cooling graph for the cabbage. It's based on data from the USDA's famous Handbook 66. We're cooling from 80 degrees Fahrenheit down to 32 degrees Fahrenheit, so our midpoint temperature is going to be 56 degrees Fahrenheit. To determine respiratory heat, a multiplier, 220, has been derived by USDA scientists, and it converts milligrams of CO2 per kilogram hour to BTUs per day per ton of product. At 56 degrees Fahrenheit, the respiratory rate is estimated to be 20 milligrams of CO2 per kilogram hour. Again, this value was obtained from the literature. So, the respiratory heat that will be produced is 220 times 20, or 4,400 BTUs per day per ton of cabbage. Since we are cooling 100 tons of cabbage, the respiratory heat during cooling will be 100 times 4,400 to yield 440,000 BTUs per day from all the cabbage. By definition, a ton of refrigeration is 288,000 BTUs of heat absorbed per day. 440,000 BTUs produced daily from the cabbage divided by 288,000 BTUs of heat absorbed per day per ton of refrigeration yields 1.53 tons of refrigeration needed to remove the respiratory heat during the cooling process. Note that, unlike sensible heat, respiratory heat calculations are unaffected by time. The value will be the same whether we are cooling for 12 or 2 hours, since the midpoint temperature during cooling will remain the same. We calculated previously that to cool 100 tons of cabbage from 80 to 32 degrees Fahrenheit within 12 hours will require 63 tons of refrigeration to remove the sensible heat. 63 tons plus 1.53 tons for the respiratory heat yields a grand total of 64.53 tons of refrigeration to cool the cabbage, and that's within 12 hours. Problem. Once cooled, how much refrigeration capacity will be required to hold the cabbage at 32 degrees Fahrenheit? Since we've removed the sensible heat, we need only consider the heat of respiration. At 32 degrees Fahrenheit, cabbage has been measured to have a respiration rate of 4 to 6 milligrams of CO2 per kilogram hour. To ensure that there is enough refrigeration, use the larger of the two values. Be conservative. It's better to have a bit too much refrigeration capacity than not enough. 6 times 220 equals 1,320 BTUs per day per ton of cabbage. We have 100 tons of cabbage, so 100 tons times 1,320 BTUs per ton equals 132,000 BTUs per day total. 132,000 BTUs per day divided by 288,000 BTUs per day per ton of refrigeration equals 0.46 tons of refrigeration to hold the cabbage at 32 degrees. To cool 100 tons of cabbage required 64.53 tons of refrigeration, but to hold it requires 0.46 tons of refrigeration. 0.46 tons is only about 7% of the refrigeration capacity initially needed to cool the cabbage. This explains why refrigeration units on trucks can be so small and still keep the product cold. It also explains why it is so important to keep cooled product cold, since it takes so much energy to cool it initially. When calculating refrigeration requirements for a facility, one must also consider heat leakage from open doors, cracks, or through poor insulation. Utility heat, that is heat from forklifts, equipment, and from your workers. Container heat, consider the number of containers, their size, and their composition. The size, that is the volume of your storage, the number of air changes per day, and the air's relative humidity. One has to cool the air as well as the water in the air. Summary points. When calculating refrigeration load to cool, not only sensible heat, but also the heat of respiration or vital heat must be considered. Respiratory heat is continuously produced by the product and directly proportional to respiration rate. During cooling, when calculating refrigeration load, we use the respiration rate of the commodity at the midpoint cooling temperature. A multiplier, 220, is used to convert the respiration rate in milligrams of CO2 per kilogram hour to BTUs per day per ton of product. The refrigeration load to remove sensible heat is highly affected by cooling time. In contrast, the refrigeration load to remove vital heat is unaffected by time, since we use the same respiration value whether we are cooling for 1 or 24 hours. Once cooled, the refrigeration load required to hold the commodity at its storage temperature is much less than what was required to cool it. When calculating refrigeration load to hold produce, one must consider vital heat and heat leakage into the storage facility, container numbers and their specific heats, the size of the storage, the number of air changes per day, and the storage air relative humidity.